Welcome to Physics Made Easy channel. The next topic is nuclear fusion, the process in which two light nuclei combine to form a single heavier nucleus is called nuclear fusion. And binding energy curve plus packing fraction curve, all of them they predict the nuclear, you can say fusion. Particularly binding energy curve in which smaller nuclei like deuterons they combine to form helium, the process by which two lighter nuclei with at extremely high temperature to form a single heavier nuclei called nuclear fusion. The mass of the heavier nucleus formed is less than the sum of the masses of the combined nuclei, and mass defect is released in the form of energy according to Einstein relationship. Now there is a mass defect, and due to that mass defect some of the mass is lost and that mass is converted into energy. Because of this, E is equal to mc square equivalence. Two protons combine to form a deuteron, and the energy releases 0.45 million electron volts. And now this is the basic reaction. One proton plus one proton, one H2 is formed and a positron is emitted, and energy of 0.42 MeV is emitted. Similarly, two deuterons combine either to form lighter isotope of helium and a neutron, or tritium or proton. Now let us see this. One H2 plus one H2 they combine to form two helium-3, a neutron plus 3.275 MeV energy, and then one deuteron and one deuteron combine, one H3 tritium and proton is formed, and 4.03 MeV of the energy is released. Now the basic problem with nuclear fusion is that we have to overcome very high electrostatic repulsion between them at extremely small distance. When distance is very small, electrostatic forces they follow inverse square law. F is equal to k q1 q2 by r square. I will write this relationship, and when distance is of the order of Fermi, you can now get an idea from here. This is k q1 q2 by r square. Now when distance is of the order of Fermi means 10 raised to power minus 15, and when it will go in numerator it will come 10 raised to power 30, and force will be very large that we need to overcome. This repulsion prevents the two nuclei from getting closer enough to be within the range of attractive nuclear forces before fusing. And for that, we need a very high temperature of the order of 10 raised to power 6 Kelvin. Now, the height of the Coulomb barrier, this repulsion has to be overcome by the kinetic energy of the nuclei that we want to fuse, because at high temperature nuclei will move with very high velocity, and then initial kinetic energy is so large that it overcomes the potential energy of the barrier. This is the basic theory of nuclear fusion. When you have to practically perform it. And now, necessary condition for nuclear fusion. High temperature is necessary for the lighter nuclei to have sufficient kinetic energy so that overcome this mutual repulsion. High density or pressure increases the frequency of collision of light nuclei and hence rate of fusion. And now, the condition exists in interior of sun. Such condition of high temperature about 10 raised to power 6 Kelvin, it exists in inside sun. So it means fusion is the source of sun energy. Now fusion as a source of sun energy and stars, I have just stated there are two cycles. One is proton-proton cycle, other is carbon-nitrogen cycle. In proton-proton cycle, we have got this nuclear reaction taking place. 1H1, 1H1, it combines to form 1H2, and then a positron is emitted and a neutrino is emitted. Or these two electron and positron they fuse to form gamma rays. So these kinds of nuclear reaction, this is one kind of nuclear reaction. For example, deuterium combines with the proton to form 2 helium-3, 5.49 MeV, and this 2 helium-3 and 2 helium combines to form a helium plus 2 protons. 12.86 MeV energy is released. Now this is the final chain reaction. This is the final reaction, not chain reaction. This is the final reaction. I will just write the final reaction. 4 protons. This is proton-proton cycle, the source of energy of sun. 4 protons combine to form twice of helium-4 plus 2 neutrinos plus 6 gamma particles plus 26.7 MeV energy. Now you don't need to go through these reactions because I have gone through them very quickly. They are not that important. This reaction, kindly try to memorize this reaction for nuclear fusion, and this is one reaction which is source of solar energy, and you can even write this reaction in your board examination as an example of nuclear fusion. The next is carbon nitrogen cycle. Carbon nitrogen cycle is a very long cycle. This is like this. And I will just write the final reaction. I will just write the final reaction. The final reaction is, you can say 6 carbon. The final reaction is, this reaction is important. 6 carbon 12 plus 4, and this article is important from board examination point of view. From need you just need to remember it. Carbon is a catalyst. 4 proton they combine to form a helium. Carbon is just a catalyst in this case. 2 positrons plus 2 neutrinos are emitted plus some gamma radiation, and this much of the energy is released. So you should just be familiar with this reaction for your examination, particularly for NEET. This is not important for JEE Main. This is important for board examination as well as for NEET, and not for JEE Main or JEE Advanced. You should just note that carbon nitrogen cycle, carbon and carbon acts as a catalyst. Proton-proton cycle, proton-proton cycle and carbon nitrogen cycle, they are the source of energy of stars. And in this case, 4 protons combine to form helium, and in this case also 4 protons combine to form helium. One is catalyzed by carbon and other is not catalyzed by carbon. So these two things that should be borne in your mind from this very part. And now there are two kinds of stars. Now, stars which are hotter than sun. Stars which are hotter than sun, they follow carbon nitrogen cycle. And stars which are cooler than sun, they follow proton-proton cycle. This is another important fact. Now, controlled thermonuclear reactions. Controlled fusion. Now, we shall be talking about controlled fusion. So, in this case, again, it is very difficult to control the fusion, because in fusion, their velocities are very high, and how will you confine them within some part because of their very high energy? And another point is, you need the temperature of 10 raised to power 6. This is possible only if nuclear fission takes place before nuclear fusion. And now this is basically a model of fusion based reactor. Here you have got hot plasma and there are magnetic lenses. Magnetic lens reflects the ray, and this magnetic lenses, they reflect the ions. And here huge amount of heat is produced by nuclear fusion reaction. First, fission is performed because you can achieve the temperature of 10 raised to power 6 Kelvin only in nuclear fission reaction. First, we perform the nuclear fission, and at such a high temperature, uh, matter is in the state of plasma. Now, this is plasma, very high speed moving ions. Now, they are controlled by the magnetic lenses here, and now here we circulate the cold fluid. It gets heated up, and this is heat exchanger, and here the steam passes to some other part, and here we have got these turbines which rotates the coils, and heat is and then final electricity is produced here. Again, cold fuel is made to enter this, which absorbs the heat of this nuclear fusion reaction. Hot fluid comes here, heat is exchanged here, and now steam goes in this part. Here, steam pushes, you can say, the turbines. And after pushing the turbines, it rotates the coil, which is put between the very heavy magnets, and electricity is produced. So, this we have a broad model of nuclear fusion uh, reactor. And now, before finishing this lecture, I will like to discuss this thing: comparison between nuclear fission and fusion. Nuclear fission: excited heavy nuclei split into two nuclei of comparable masses. In fusion, two lighter nuclei, they are suitably excited and they fuse together to form a heavier nuclei. In this lighter nuclei, they combine or fuse to form heavier nuclei. In case of fusion, in case of fission, heavy nuclei split into two nuclei of comparable masses. In both these reactions, huge amount of energy is released. Energy produced per fission is per nucleon is very small. This is 0.85 MeV. How we arrived at this figure is you just divide 200 MeV released in nuclear fission by 235 nucleons. We get this much. And energy produced per nucleon in fusion is very high. Now, fission can be performed in laboratory, but it is very tough to perform in laboratory. Fusion is very tough to form in laboratory. The condition of high temperature and pressure are not required in fission. In fusion, high temperature and pressure are required to overcome Coulomb forces. And the next is the fissionable materials are limited, but fusible material are in abundance. That's why this world is trying nuclear fusion to take place. Neutrons are intermediate particles. In fission reaction, neutrons are intermediate particles. In fusion, their protons are intermediate particles. It's a fast process. It is composed of many steps. There are many steps in it. It causes pollution. Fission causes pollution, and it is harmful. Fission causes pollution, and radio radio waste. We have to tackle this problem, and it is environmentally safe. Fusion is environmentally safe. The material required for fusion is in abundance, while that required for fission is very rare. Fusion is a multi-step process. Fission is a fast-step process. Fusion, proton is the intermediate particle. In this case, neutrons are intermediate particle here. And another important fact, we need very high temperature to overcome Coulomb repulsive forces. We don't need high temperature in fission. Fission can be performed in lab. Fusion cannot be performed in lab. And energy emitted per nucleon is more in fusion than in fission. Now, another important difference which has been left out: in fission, we need critical size and critical mass. in fission, we have the concept of critical size and mass. Here, in this case, we just fission is to be performed. There is no concept of critical size and critical mass. Fission is performed before fusion. The first fission is performed, high temperature is generated, then fusion is attempted. And in fusion, there is no concept of critical size and critical mass. It means the concept of critical size and critical mass is only required in fission. In fusion, you just require very high temperature. With these words, before finishing this lecture, I will request all of you to kindly view the video, and if you like it then share it. If you don't like it then kindly comment so that we can improve this in future. So with these words we have done with this chapter of nuclei, and as many of the students they are demanding that I should come to MCQs. Obviously, I will solve some MCQs, but before that, I want all the students to go through the basics and NCRT exemplar problems. NCRT exemplar are the basis for your competitions, particularly NEET and JEE Main. Anybody who has not done NCRT, I think he will find it very difficult to clear JEE Main or JEE Advanced and NEET as well. With these words, I finish this lecture and thank you very much.